Okay. So lattice energy, so it's going to be the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ion under standard condition. So if I want to write down, for example, the lattice energy of aluminium oxide, for example, okay, so this is going to be solid, okay, and then you are going to form from its gaseous ion, so Al, okay, 3 plus, and then O2 minus, okay, so gas must be gas, and then you adjust accordingly, okay, like when you balance, there are 2, so you put 2 there, okay, there's 3, and then you put 3 over there, okay, quite simple, okay, this is going to be lattice energy. So if you move on, okay, so like for example, give values for standard condition of temperature and pressure, because we always use standard condition. So what does it mean? Okay, the standard condition, the pressure and temperature. Temperature is 298 Kelvin. And then the pressure is normally it's 101,000 kilopascal. But in your syllabus, we just change it into, make it simple, 100,000, or which is 100 kilopascal. Okay, so we make it like that. Okay. Write equations describing lattice energy of this. Okay, you can refer to all these examples. Maybe I will just do one example for potassium bromide. Okay, KBr, okay, is going to be solid, and then I am going to form from K plus and then Br minus, okay, and then they must be in gaseous state. So make sure, okay, you know how to write these expressions or equations, okay, related to lattice energy. Next, we also have learned about the definition of enthalpy change of atomization. Okay, so if you look at the enthalpy change of atomization, it's going to be the enthalpy change, okay, when 1 mole of gaseous atom is formed from its element under standard condition. Okay, so you are forming, okay, 1 mole of gaseous atom from element. So this is going to be 1 mole of gaseous atom from its element. The element, which is going to be lithium, which is going to be metal, it is going to be solid. So you write down over there, okay, this is going to be enthalpy change of atomization. Some other examples, okay, if you look at Cl2, okay, we know element is always in form of Cl2. U1, okay, enthalpy change of atomization. So you want 1 atom of Cl, which is in gaseous form. So how to make sure, okay, I don't put 2 over there. You just need to put half over there. And then this is also going to be in gas, okay, under standard condition. And I also told you, okay, if you have Cl2, okay, Br2 and I2, you need to know this one. You already learned group 17. Okay, Cl2 is gas at room temperature. Okay, Br2 is going to be liquid, and then I2 is going to be solid. Okay, so if I want to write down enthalpy change of atomization of iodine, for example, 1 mole of gaseous I, okay, atom, okay, you are going to get from half I2, okay, but it must be the element. The element at that standard condition for I2 is going to be solid. So you need to know this, okay? Make sure you know how to write, okay? Next is going to be this one. I think yesterday, okay, we learned about this, okay? This one, I hope yesterday it's your class, but if it is not your class also, I will repeat again, okay? This one related, like for example, okay, sometimes, okay, when we deal with atomization, okay, like for example, if I want to put Cl2, okay, so Cl2 break into Cl, okay, and then you have half Cl2, for example, gas, and then change it to gas, okay. This is going to be the enthalpy of atomization. Enthalpy of atomization, let's say HAT, so it's going to be, let's say I give you a number 124, okay, 124. But sometimes, okay, they will not give you this enthalpy of atomization. Okay, that doesn't mean the question is wrong. Okay, that doesn't mean the question is wrong. You can still get or solve, okay, this, okay, or try to complete the Born-Haber cycle, okay, by referring to your bond energy. Okay, the bond energy, you can refer to your data booklet. Okay, you can refer to the data booklet. You just look at the bond energy. What is bond energy? It's the energy required to break the bond. Between what and what? Okay, you go and look for Cl and Cl. Okay, and they will give you, okay, the bond energy is, they give you a value. Okay, they give you a value. And this value, okay, is going to be, it depends, okay, it depends. But I'll give you the value. Let's say based on my, this number, it might be 248. Okay, this might be 248. And how do I use these numbers, okay, to help me to write down, okay, which one is suitable, which one is what, okay? If you are doing, like, for example, half Cl2 to change to Cl, okay, then you are forming 1 mole of atom of Cl. You use 124 atomization, okay, 124. But what happens if, let's say, I have 3/2 Cl2, let's say a situation, 3/2 Cl2, and then you are forming 3Cl. Let's say it happened to be, I think if someone have done the AlCl3, you will know what I mean, the Bornhaber for AlCl3, yeah? So if, let's say, you have 3/2 Cl2 and I want to get for 3Cl, yeah, I want to get the 3Cl, gas and gas. If I have enthalpy of atomization, what I should write down? Okay, I should write down 3 times 124. Why 3 times 124? Because I am forming 3 moles of atom of Cl. Okay, so 3 times of atomization. But let's say the enthalpy of atomization is not given, but you still have 3/2 Cl2 to give you 3Cl. And you refer to the data booklet and you found out the bond energy. What is the number that you're supposed to use? The number that you're supposed to use is going to be 248, but you need to do something. You need to times, but you do not times by 3. No, you don't times it by 3. You times with this number, 3/2 times. Please remember this, okay? Because you are breaking the bond between Cl and Cl. How many moles of Cl and Cl you're breaking? You're breaking 1.5 moles of Cl2. So you need to break, you need to times the 1.5 times 248. Okay, that's the difference. Okay, bond energy, and if you are using enthalpy change of atomization, very, very important. I hope you really understand about this. Now, this is going to be, this question is like something related to that. Okay, the bond energy of chlorine molecule is 244. Why is the standard enthalpy change of atomization is half of this value? Similar, Cl and Cl, bond energy, you break this, you are going to get 2 Cl atoms. And that is 244. And if you want the enthalpy change of atomization, atomization is supposed to be half Cl2 to give you Cl, gas and gas. You want only 1. So 244 is for 2. So 244 divided by 2. That's the reason. Okay. And that's the reason why I explain about this and I explain about this. Okay, please take note. Okay, write equations including state symbols that represents the enthalpy change of atomization for the following. Okay, this one, okay, you can refer to here. Okay, so every single time 1 mole of atom. Okay, and then you follow the standard condition. Oxygen is gas, barium is solid. Okay, Br2 is going to be liquid. Sometimes they will ask you, what is the numerical value of atomization of helium? If let's say not helium, I'll give you another example, neon. Okay, if you have monoatomic elements, okay, helium, neon, okay, all the group 18, okay, if you have all of those, okay, you if they ask you what is the atomization, because it's supposed to be giving you 1 mole of atom, gaseous atom, and they are already gaseous atom. Okay, if they are already in gaseous atom already, so the answer is going to be 0. Okay, why? because they already naturally existing as single gaseous atom, so no change will be involved. Okay, so this is going to be one thing that you need to also give attention to. Okay, Nevan, until here, can you follow?
Yes, sir.
Okay, so let's move on to electron affinity. Okay, the electron affinity is happening for gases non-metal. Yeah, so this one, remember I told you we will focus group 15, group 16, and group 17. Yeah, so that's why they say gases non-metal, except one electron called electron affinity. Okay, the symbol is going to be like that. So this one, they have given you the explanation or the definition for the first electron affinity. When 1 mole of electron is added to 1 mole of gaseous atom, very important, to form 1 mole of gaseous 1 minus ion under standard condition. So if I give you one example, Cl, okay, is in gas. When I add 1 mole of electron, I am going to get Cl minus, and it is going to be in gaseous form as well. So this is going to be the equation for first electron affinity. But the second electron affinity is Cl minus. If I have the gas, okay, when I add another electron, I am going to get Cl2 minus, which is also in gas. So that is going to be my second electron affinity. Okay, what you need to take note is, okay, your first electron affinity and the second electron affinity and the third. Okay, if let's say we happen to have the third one, Cl2 minus gas plus electron to give you Cl3 minus gas. Okay, the first electron affinity is going to be, because we are talking about adding the electron. Okay, you are adding the electron, you are forming bonds, so they are going to be negative. Okay, but for the second and third, okay, in your syllabus, let's focus on your syllabus only. Why the energy is going to become not negative? Why now is positive? The reason is you are adding negative charge into negative ion. Okay, so the extra energy is required, these two, the extra energy is required to overcome the repulsion. Okay, to overcome the repulsion between opposite, okay, between opposite charge. Okay, opposite charge. Sorry, between the same charge. Okay, so when I check, I think I have given you some feedback, okay, of the 4 groups that submitted to me. I think the one that without any error or something, I think Dylan's group, yeah, Dylan's group. So the others, I think maybe when I give the feedback, some of you already corrected, okay, but you need to mention, okay, why the first one is negative, the second and third, why is positive, because the energy is absorbed to overcome the repulsion between the same charge, okay, of the ion, negative ion, and the negative charge of the electron. Okay, so you need to mention about that. Okay, that is about this slide. Okay, you can just go through it. Yeah. Now, so here, even you see, okay, these are some of the example of questions that they will ask you. Okay, why the second and third electron affinities are always endothermic? Okay, the reason, there must be input of energy to overcome the repulsive forces between electron and negative ion. Okay, like what I've written over here. Okay, now, if let's say some calculations, they say first electron affinity is negative 200, second electron affinity is that, calculate this. This is very simple. Okay, why I say very simple? First electron affinity, sulfur plus electron to give you S minus. S minus plus electron to give you S2 minus. They want, okay, S plus 2 electron to give you S2 minus. So you need to add these two equations only. Okay, when you add this equation, okay, this is going to become 2 electron. This S minus and S minus will cancel. You will get sulfur, okay, plus 2 electron to give you S2 minus. Okay, that is what we were looking for. So if this is negative 200 and this is positive 640, so what is this? Okay, this is obviously you just add these two, okay, which is going to be, you are going to get 414. Okay, that's going to be the answer. Okay, but starting from now, please be careful. If you have a positive value, always don't forget to put positive. Okay, don't forget. Okay, so this one I think we need to learn. Okay, we need to learn how to write it down. If let's say here I want to write down the second electron affinity of sulfur, okay, so I'm adding the second electron. So first is already added, so sulfur, okay, so I add another electron to become second. Okay, so this one must be in gas, even though they didn't tell for ionization energy and electron affinity, even for other situations like lattice energy and so on. If they give you 2 marks or 1 mark, okay, and then they ask you to write the equation, if you do not write the state, automatically it's wrong. Okay, please remember that, because the state is very, very important, okay, when it comes to the equation involving the definition. Okay, so even though you write down and you can argue why it's only 1 mark, sir. Okay, and then I thought that normally if they want state, they will say in the question. Normally they don't say, okay, only during our school test only I will tell my teachers to say, okay, but in the actual situation, okay, non-prelim, in the actual paper, they don't say. If they give you 2 marks, automatically they are testing you on your state. But sometimes, okay, I've seen many questions, they test about ionization energy and also lattice energy. They ask you to write the equation and they give you only 1 mark. No need to say state the symbol. Okay, they will not say that. Automatically, if you write everything correctly, but no, you balance everything correctly, but you didn't write the state involving definition, okay, any kind of equation that do not follow that, automatically it will be 0. Yeah, so this one I let you know. Okay, now I think as you are preparing for your AS exam and so on, yeah, I will let you know all this. Okay, you need to learn. Yeah, so don't lose marks just like that for those kind of things. Okay, all these please go through. Okay, first ionization energy, how to write, enthalpy of formation, how to write. You should be able to come out with the ways how to write. Even this one, calculating the lattice energy of sodium chloride. This one you need to learn how to draw the Born-Haber cycle, and then you can find out the lattice energy for the sodium chloride. Okay, maybe we have time, so I'll just show you how this one can be done. So you can see the formation is negative 411. So first thing you put over here, okay, to form NaCl, okay, NaCl solid, okay, you are getting it, okay, you're forming it from sodium, okay, sodium solid, and half Cl2, which is going to be gas. Okay, that is enthalpy of formation, negative 411. Okay, I write down. Second, okay, I have atomization value, so I'll just change it into atomization. So maybe I draw like this. I put the arrow over here. And then I'm going to change sodium to become gas. Okay, so this is going to be my atomization of sodium. So that is going to be 107. I already atomized it. Okay, let's atomize Cl. Okay, I'll just put another line over here. Half Cl2 is going to become 1 Cl. Okay, so you do not need to rewrite anything. Just put any gas and then Cl gas. And this one is going to be 122. Okay, so now, okay, you have done this. So you have the ionization energy of sodium. You want to change it into Na plus. Okay, so just put another one. And then this is going to change into Na plus gas. Cl stay as it is. Okay, make sure, okay, this one Na plus means they are going to give you electron. Okay, you remove, okay, 1 electron. So the electron will come here. Okay, so this is going to be the first ionization energy of sodium, which is going to be 496. So you write down 496. Then you are going to have, okay, electron affinity. You need to change the Cl into Cl minus. So this electron and the Cl will join. And do remember your first electron affinity is always negative. So you just go to the right a bit, and then you just extend this a bit. Okay, and then just show this one fall down. Okay, and it falls down negative 348. So I just put negative 348, and it will become Na plus gas plus Cl minus gas. Okay, the electron already joined with the Cl. Okay, no more electron anymore. And then you just make it longer here. Okay, if you want, okay, you can bring the NaCl here, okay, to the center of the line. Okay, and then you draw, okay, from here to here, okay, from ion and gaseous ion to form the solid 1 mole of solid ionic compound. Okay, this is going to be your lattice energy. So if I want to calculate anything over here, you have all the data over here. You just use the clockwise equals to anti-clockwise. Okay, so here I can see this one. If I put a circle there, okay, I can see that this is clockwise, 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 clockwise. Only negative 411 is going to be anti-clockwise. So I'll just put negative 411 equals to 107 plus 122 plus 496 plus negative 348, okay, plus lattice energy. So what you need to do, you just need to find out what is your lattice energy. Okay, you solve this, automatically you are going to get the negative 788. Okay, now one thing that I miss over here is, okay, in this PowerPoint slide and so on, I think you need to also take down the note saying that, okay, lattice energy is always negative. Okay, it's always negative. Why? Because it involves formation of bond. Yeah. And then when you look at atomization, okay, you are breaking bond. So therefore, it's always endothermic. Okay, always endothermic. And when you look at electron affinity, okay, I don't know whether they mention about ionization here, but ionization energy is going to be endothermic as well. Okay, but let's talk about electron affinity. Electron affinity, they will follow like the first one negative, then the rest is positive. Okay, and then ionization energy, I think they spoke somewhere here. So maybe I'll just put, if it is going to be ionization energy, ionization energy always, okay, because it's breaking the bond. Okay, so therefore it's going to be always endothermic. So you need to know all this first. Okay, this is very important for today's lesson. Yeah. Now, if you look at the Born-Haber cycle, okay, we can have a look. Okay, this is going to be how you draw the Born-Haber cycle for lithium fluoride. Okay, you can just first, okay, this is going to be enthalpy change of atomization of lithium, then enthalpy change of atomization of this one is not atomization because you see Li to Li plus, so it's a first ionization energy. Okay, first ionization energy of lithium. And then here, okay, from this F2 to become this is going to be atomization, okay, of F. And then here, this is going to be from this one joined together, electron affinity. And then lattice energy, and you can calculate, okay. If you look at this magnesium chloride, okay, so magnesium chloride is MgCl2, okay. So you see here, okay, the assumption, they made the assumption, okay, enthalpy of formation is going to be negative. So they show, okay, this one solid, so negative, they are going to be solid and gas. So what they did first, you need to atomize it. So they become Mg gas. Then after that, you can atomize in this case, they don't do atomization of Cl first. They ionize first. But do remember, they ionize and get first ionization energy. It means they are changing into Mg plus first. Then only you get Mg2 plus. Okay, you need to do it twice. I think yesterday some of the groups actually go and say 2 times. It's wrong. Okay, so it must be ionization energy first and then second. Okay, once you get this, okay, now you are going to atomize the Cl. Okay, here you can see they need 2 Cl. Okay, so atomization is for 1 mole of Cl. If you have 2 Cl, then 2 times atomization. Okay, you times by 2. Okay, for 2 moles of gaseous atom. Okay, so once you get that, then you remove you add the electron, but you are adding the electron for 2 moles. So it must be 2 times, okay, electron affinity. Okay, 2 times electron affinity. Sometimes be careful, okay, sometimes if you have O2 minus, okay, this one, even though they have 1 mole, okay, you have to add electron to become O minus, and another one is to make it into O2 minus. Okay, that will result in having one negative, and then this one to form O2 minus, maybe they need to go up a bit. Okay, because the second electron affinity is positive. Okay, so please take note of that. Okay, once you have done, okay, you will get the answer. Okay, so if you do not follow these two, if you do not follow these two properly, okay, will I get full mark? Okay, if they ask you to calculate anything, too bad, yeah. If they give you 4 marks, okay, and you don't follow, okay, maximum you can obtain, okay, it's going to be 2 marks out of that 4, okay. But that doesn't mean the rest of the question, if you get all this and then they still use the information from here for the rest of the question, are you going to get everything wrong? The answer is no. Okay, you will only be deducted the part that you made the mistake, but we will assume whatever your answer that you give is correct, and you will use the same answer, and the working you get your own answer, which is different than the marking key. For the rest of it, it is still considered correct and will be given full mark. Okay, so you will only lose over here, but that doesn't mean that, okay, you can make mistakes. No, I don't want you to make any mistakes. Okay, so please be careful related to all this. Okay, drawing. Okay, I think by now you should be able to draw. Okay, this one and this one also. Whenever you look at the enthalpy changes, okay, you should be able to see and tell what type of enthalpy change is this. Okay, so maybe I'll just test you over here, Josh. Okay, can you tell me the 5B1? What type of enthalpy change is that?
Enthalpy change of atomization.
Okay, this is going to be enthalpy change of atomization of iodine. Okay, so Jordan, can you tell the second one?
The second one, electron affinity.
Okay, gas to gas, you add electron affinity. Clienta, can you tell for the third one? Maybe internet problem. Clienta, are you there?
Not sure, sir.
Not sure. So maybe someone can help. Maybe Kiara, can you help?
Formation.
Yeah, this is formation. You see, solid 1 mole. Okay, you're forming it from the elements. Okay, from the elements. So formation. And then here, this is going to be ions and forming 1 mole. So this one, Michelle, what is this?
Formation.
No. Ions and they are gas. Okay, ion and gas. You see, ion and gas, they give you. So this one is going to be lattice energy, Michelle. Yeah. So this one is going to be lattice energy. So make sure you know how to differentiate all of them. Okay, very important. Okay, so today, okay, this is the lesson for today. So we will learn about, okay, the factors affecting the lattice energy. Okay, so there are 2 factors affecting lattice energy. So if you look at lattice energy, what is the definition of lattice energy? If you have a positive ion and they are in gaseous form, if you have a negative ion and they are in gaseous form, when they join together, they are forming bonds. Okay, so when they are forming bonds, they release energy. So basically, they're talking about energy because forming bonds. Okay, so the factors that will affect lattice energy must be whether, okay, how much energy that is going to be released might be depending on how strong the formation, okay, the bond formation is. Okay, so when can we say the bond formation is very, very strong? Okay, one, okay, when the size, okay, is going to be small. Okay, please remember this. Okay, if the size is small, okay, if you have a particular charge, okay, and the size is small, okay, what happens is this positive charge, okay, is shared with a smaller volume. Okay, is shared with the smaller volume. If you have a bigger volume, okay, a bigger molecule atom, and then you have positive, the same positive charge, they are going to be shared across a larger volume. So overall, what can we say about the strength? Because they are going to be shared across, okay, so the attraction, okay, or the positive charge is not that strong compared to the one that has the smaller volume, okay, smaller volume. Just remember like this, right? Maybe Dylan has have to study tomorrow for 2 tests, for example, okay. So you need to give attention for 2 tests, okay. But suddenly Kenneth have to study for 3 or 4 tests tomorrow, yeah. So the attention, okay, will be greater, okay, when it comes to Dylan, because he just focus only on 2, okay. But Kenneth have to divide his attention into 4 tests, okay, which is going to be more, okay. So you are not going to have the full attention to it, okay. So the same applies over here. The positive will be more. So if I have a negative charge, any kind of a negative ion coming in, the bond will be more greater, okay, will be more greater compared to the negative charge over here. It's not going to be that great, okay. So when it is small, okay, you are going to form more bonds, okay. When you have more bonds, it means you are talking about negative, okay. So it will become more exothermic. Bond forming is exothermic. So you can see here, okay, when the size increases, okay, when the size increases, okay, it means that, okay, you are going to share it with a bigger volume. So you are not going to form a very good bond, okay. If you don't form a very good bond, okay, it means bond formation is less, okay. If bond formation is less, it will become less exothermic, okay. So they don't give you a lot of energy out, yeah. So less exothermic because of that, okay. But how do we mention it in a proper sentence? Okay, you mention it like this, okay. We call it as charge density. Okay, density, I think you know, everyone knows what is density, mass over volume. Okay, so in chemistry, we use this term charge density. So what is charge density? Okay, you just replace the mass, you put charge over volume. Okay, charge over volume. And most of the time, okay, volume of any atom is going to be difficult to identify. So you just say volume is directly proportional to radius. Yeah. So if assuming the atom is a sphere, so sometimes, okay, charge density is also charge over radius, okay. So whatever it is, okay, if you have, okay, for example, okay, you have a bigger molecule, bigger atom, the charge density is lower. Why? Because charge divided by bigger volume, okay, charge divided by bigger volume. So if this is bigger, something divided by something that is bigger, okay, you are going to get less value, okay, which is going to be the charge density is lower, okay. Because charge density is lower, they cannot form a proper bond with negative ion. So it will result in weaker electrostatic force of attraction, and that's why it's less exothermic. And it will be vice versa, okay, when it's going to be size is going to be smaller, okay. So that is about size, okay. Now, since we are talking about the charge density, there is another factor as well, okay. Just now, the only thing that is changing is the size. But how about charge, okay, because we are talking about charge density. Charge density got related to your volume, which is related to the size. And it is also related to your charge itself, okay. What happens if I have Na plus and if I compare with Mg2 plus, is there any difference? Okay, of course, the difference is there. One is with positive 1, another one is positive 2, more charge. If you have more charge, of course, a negative ion try to come in, they will form a stronger bond. Okay, they will form a stronger bond. If the stronger bond is formed, then you will get more exothermic. Okay, more exothermic. So the ionic charge increases, lattice energy will become exothermic. Why? You need to mention in terms of charge density, greater the ionic charge. Okay, what is charge density? Charge divided by volume. You have more charge. Okay, so higher charge density. and it will result in stronger ionic bond. Okay, the bond between positive and negative will be more. Okay, when it is stronger, then you have more exothermic. So that is going to be about, okay, the factors affecting lattice energy. So let's now we compare. Okay, we compare. So compare the lattice energy between magnesium oxide and lithium fluoride, and compare the lattice energy of lithium fluoride and magnesium potassium bromide. So how to compare? Okay, MgO and LIF. Okay, so how do we compare? Kendru, can you try over here? MgO and LIF, which one do you think more exothermic? Both of them will be exothermic. Which one will be more exothermic, Kendru?
Mg.
Yes, okay, related to Mg. Why? Because when LIF, you're dealing with Li plus and F minus. Mg, you're dealing with Mg2 plus and O2 minus. We are talking about charge. Okay, more charge density. Okay, if you compare 2 plus and plus, okay, more charge density. So the attraction between these two will be way greater compared to the attraction between these two. Okay, so that will release a lot of energy. So they will be, magnesium oxide will be more exothermic. Okay, more exothermic. Now compare the lattice energy of lithium fluoride LIF and KBr. If you notice over here, Li plus, F minus, K plus, Br minus. The charge are the same. So you need to compare the size. So which one? Okay, which one will give you a more negative value? Nevan, can you try?
Yes, sir.
Can you try which one will be giving you a more negative value? Lithium fluoride or potassium bromide?
Lithium fluoride.
Okay, why? Okay, you see group 7, FClBri. Okay, F is smaller. Okay, Br is bigger. Okay, going down the group is supposed to be smaller to bigger. Okay, lithium and potassium also, lithium is at the top, potassium at the bottom. They are smaller, and then this is bigger. So we are comparing, okay, smaller and bigger. Okay, they have the same charge. Okay, so the one that has the same charge, and if they are smaller, okay, the charge density of LIF, okay, LIF is going to be more. Charge density is more. So if the charge density is more, okay, because the charge is spread over smaller volume, and that will result in bigger or more stronger electrostatic forces of attraction, okay, between the Li and F, okay, Li plus and F minus, and that will give you a more exothermic. So you can see the answer, okay, MgO higher, rather than saying higher lattice energy, I think it's better to say more negative lattice energy, okay, or more exothermic. Okay, and then LIF is going to be lithium fluoride, is going to be more exothermic as well. Okay, so you need to know about this. Okay, so we have 10 minutes to introduce new things. Okay, so this is new things. So what extra? Yeah? So earlier we did revision. Okay, the first period we did revision. Then I teach you about factors affecting lattice energy. And now, okay, we are entering the part new things. Okay, coming back to new enthalpy changes. Okay, you see, we are going to learn about, okay, enthalpy changes of solution. Okay, what is enthalpy change of solution? Enthalpy change of solution is going to be the energy absorbed or released. So you see, it's going to be, it can be positive, it can be negative. Okay, when 1 mole of ionic solid dissolve in sufficient water to form a very dilute solution. Okay, so if you're talking about ionic solid, so I think the common ionic solid, NaCl, okay, this is solid. When you dissolve in a lot of water, I'll just put AQ, no need to put H2O, AQ. They are going to dissolve, so they give you NaCl, you can just put AQ, aqueous. Okay, so this is going to be the equation, okay, for enthalpy change of solution. But sometimes you can also write it down as NaCl, solid plus aqueous. Okay, when they are aqueous, they can actually separate into their individual ion, which is aqueous also. Okay, this is also accepted. So you can use any of these two, okay, to write the equation for enthalpy change of solution. Okay, so enthalpy can be either positive or negative. Okay, but okay, let us look into the definition properly. Okay, if I have NaCl, if I put NaCl, NaCl, they are going to be a giant lattice. Okay, if I just put over here, and then that's the reason why the boiling point and melting point is quite high. Okay, NaCl, okay, in solid form, a giant ionic lattice. So what we are doing over here is when I add water, okay, when I add aqueous H2O, okay, what happens? Okay, the H2O, okay, you can write it in this way, HOH. They are delta negative, they are delta positive here. So the delta positive will go and attract, okay, will form some kind of bond. This is called ion dipole. This is 2, so it's called dipole. Cl minus is ion, so this bond is called ion dipole bond. Okay, so when they put this, when they come closer to this water, what will happen? This water will say, Cl, say bye bye to your NaCl, you follow me. Okay, they try to attract. Okay, the same thing. Okay, when you have water, another molecule of water, I'll just copy the same thing here. And if I have it over here, okay, and if I put, okay, this is delta positive, okay, the negative oxygen, they will also have, this is ion and that is dipole. They will form a bond and they will say, water will say, sodium, you leave your NaCl and you follow me. So that is how the Na plus and the Cl minus is going to be formed, okay, dissolve in water. Okay, so what happens over here? You are talking about, okay, let me actually ask someone over here. Jonathan, are we talking about bond formation or bond breaking? Enthalpy change of solution.
Is it bond breaking?
Depends on how you are looking at. Are we looking at ionic lattice or are we looking at water? Because if you look at the equation, we are looking into what? We are looking into water. Yeah, something add with water and you are forming according to the definition to form. Okay, it's going to be when you dissolve in sufficient water to form a very dilute solution. So you are looking from the perspective of water. So is are you forming bond with water or breaking bond with water?
Forming.
Forming. Okay, you're forming bonds. Okay, therefore, because it is involving bond forming, it is going to be negative. Okay, it's negative. So if there is proper bond breaking, forming, okay, or negative, it means that they are saying bye-bye to each other. No more NaCl, I'm just following water. Okay, but if let's say your value is not negative, okay, your value is not negative, it means that they cannot say bye-bye to their ionic form. Okay, they have to stay. They do not form bonds enough, okay, with water. Okay, so they don't dissolve. So that is why we can explain over here, it is soluble if the enthalpy change of solution is negative, bond forming with water. And okay, if you have a small positive value, what is small positive value? Maybe positive 4, positive 3. It's considered to be small positive value. That is also, we can say it is soluble. Okay, we can say it's soluble. But if you have a large positive enthalpy of solution, it means that they are not forming bonds properly with water. Okay, it means that they are not going to dissolve. Water is not able to separate you from the friends. These are the friends. Okay, water is not enough, okay, to actually separate you. Yeah, so they don't dissolve. They stay as the giant ionic lattice. Okay, So this is going to be very important because, okay, this is going to help us to understand more, okay, about solubilities, okay. So you see here, write the equation, okay, to represent the enthalpy change of solution of potassium sulfate and zinc chloride. Very easy, yeah. I'll just show you for K2SO4, okay. So for K2SO4, you add, okay, it's a solid, you add aqueous, okay, and then they are going to give you K2SO4 aqueous. You can write it like this, or you can write K, 2K plus and SO4, 2 minus and put aqueous and put aqueous. That's it. You can refer to here. Okay, you can use any of these to write the solution. Okay, now if I want to compare the solubility over here and which one is more soluble, the moment you see this, okay, can you tell me which one is the one that is soluble? James, can you tell me which one is soluble?
Silver chloride.
No.
Wait, no. Wait.
It means you are forming the bond with water, right? So it's supposed to be positive or negative? Bond forming.
Negative.
Yeah. The only thing that is the only thing that is negative. Yeah, the only thing that is negative is sodium bromide. Okay, you must know by looking at this value. Okay, so that is the one that is soluble. Okay, must be soluble. Second that you can look is something that is going to be slightly positive, small positive. Okay, so I can compare. This is the small positive. So this one is possible, soluble. But these are big positives. Okay, if big positive, they are insoluble. And you need to know also, okay, using this data, okay, I know they are insoluble because even without looking at the data, I know silver chloride. Okay, I should know what is the color also, the precipitate silver bromide. You need to know the color also. Okay, so let's see whether you guys remember the color. Okay, Jonathan, can you tell me what is the color of AgCl?
Is it yellow?
No. Okay, remember, yeah, your AS is coming here. White precipitate. Okay, it's very important for your AS. Okay, AgCl, white precipitate. AgBr is going to be cream precipitate, and AgI is the one that is going to be yellow. Okay, please go and read more about this. Okay, then I also taught you about when you add dilute ammonia, when you add concentrated ammonia, what will happen. Please go and read. Okay, but now, okay, you see big value of solution. Okay, you are not going to able to dissolve. Okay, now there is another one, what we call enthalpy change of hydration. Okay, now you see, I'll give you a simple situation. Okay, James, let's say James is a businessman. Okay, he bought something, okay, for 100,000. Okay, he bought something for 100,000, and suddenly because of the pandemic, he cannot sell that stuff. Okay, and cannot look into profit. Okay, his business got affected. Okay, if I ask James, okay, James, your business got affected, sell this stuff, okay, 10,000 to me. James, will you sell it to me?
No.
You will rather keep it for yourself, right? Okay, rather than losing so much of money. Yeah, the same applies. Okay, the same applies to this situation where you have lattice energy. You see, lattice energy is you are bringing in the gas ion. Okay, you have another positive gas ion, negative gas ion. You bring in them, and you form a lattice. Okay, you form a lattice. And let's say you spend about -788 for it. Okay, you spend about 788 for it. And using water, which is your solution, the water start to come in. They say, come on, you follow me. Okay, you break from your lattice. Okay, but they are giving you only 3.9. They only give you 3.9. Will this break because of just 3.9? Justin?
It's small.
It's small. It's not possible to break because of 3.9. You need at least, okay, up to 788 to be able to break. But everyone knows sodium chloride, when you add water, they dissolve. So where the extra energy comes from, it must be coming from something else, okay? Not only from the solution. That is the one we call as hydration, okay? There is another one that is involved over here, okay? It's not complete yet. Okay, where is the extra money? Where is the extra amount that is missing? That amount is coming from the hydration. So what is hydration? Okay, the hydration is going to be is the enthalpy change when 1 mole of specified gaseous ion dissolve in sufficient water to form dilute solution. So it's like any gas, Na gas, okay, and ion, you add aqueous and they become Na plus aqueous. So that is extra. Okay, that's another one. Okay, and this is involving, okay, it's involving forming bond with water. Okay, so since it's involving forming bond with water, it's exothermic. Okay, it's exothermic. So it will be more exothermic, okay, when they have smaller radius, okay, more charge. I think you should know, yeah. But later I will teach you more about this, okay, teach you more about this because there is an equation for this. You can join lattice energy. You can join the solution, okay. Remember the lattice energy just now -788. This one is positive 3.9, okay. There should be a hydration. You join together. You will form a Hess's cycle, okay. You will form a cycle. When you form this cycle, okay, you can use the Hess's law to come up with an equation. And that equation, okay, you see clockwise equals to anti-clockwise, lattice energy plus solution will give you the hydration. Or you can memorize this formula, okay, by remembering let your soul go and hide. Okay, so how do you let your soul to go and hide? Okay, let, okay, is lattice, okay, soul, it was here, okay. So you let it go. So when you let it go, you bring it over here, it's negative soul. Okay, negative solution, and then and height. Okay, so plus height. So lattice energy is hydration minus solution. Okay, if you want to remember that, or if you found out a way to memorize this formula, up to you. You don't want to memorize, you want to use this, up to you. But I will discuss this during our class next time. Yeah. So that's it for today. If you have any question, okay, please message me. Okay, but if you want to get, okay, this one I didn't share it to you. Yeah, I put everything in our Google site, so please go and download over there. Okay, the PowerPoint is already updated over there. Okay, so I'll pass it to Mr. Rufus. Okay, Mr. Rufus, you already become host, right? Okay.
Yeah.
Okay. See you guys. Okay, bye.